Hi guys, this is the first of the videos that I'm going to be asking you to watch in place of class on Thursday, November 6th. So this would be the first video, and you'll have a couple more that will be uploaded to cover. So in this first one, we're going to practice actually solving one-way ANOVAs using two different methods. And remember that a one-way analysis of variance is the test that we do when we have one independent variable, but we have more than two groups. So we have 3, 4, 5, whatever number of groups in the independent variable, and we have one dependent variable. Right, so there are a couple ways that you're going to see one-way ANOVA problems appear to you. And one way is going to be when we have an ANOVA source table, which is always going to be a part of the solution that we do for ANOVAs. One way that you'll see these problems is when you're given some information already in the source table, and you're asked to use that information to fill in the rest of the open cells. And so knowing how these different cells relate to one another can help you fill in when you're just given a couple numbers already there. So in this first practice problem, we can look at the PowerPoint here, and we see that the following is a one-way ANOVA summary table with part of the material missing. And so we're going to work on filling in the missing values in the table first, and then we're going to answer the following questions that are listed here. How many groups are in this experiment? Assuming an equal number of subjects in each group, how many subjects are there in each group? What's the F-crit value if alpha is 0.05? And is there a significant effect? Okay, so we're starting with two sums of squares filled in. We have sums of squares between, and we have sums of squares total, and we're starting with 2 degrees of freedom already filled in. We have degrees of freedom between and degrees of freedom total. And using that information, we can fill in the rest of the blanks here. So we'll start with sums of squares within. Remember that sums of squares total, this number right here, is equal to sums of squares between plus sums of squares within. So to figure out what sums of squares within is, let's go over here to the PDF handwritten file, and you can see I've kind of written down the formula for how we're going to do that. We're going to take our total minus our between. So we're going to take sums of squares total value and subtract sums of square between value, and we end up with a 0.3762.72. And so what we would do with this value here is we would write it in sums of squares within. Next, we're going to work on degrees of freedom within. And we can figure that out, again, by knowing the relationship between degrees of freedom total and the degrees of freedom between and within. So degrees of freedom total is equal to degrees of freedom between plus degrees of freedom within. Okay, so to figure out our missing value, I'm going to take degrees of freedom within is equal to the total minus between. So we have 39 in total and 3 minus 3 between, so we end up with 36 degrees of freedom within. And so we can put a 36 into this empty cell here. Alright, so once we have that, we can now, once we have all of these cells filled in, we know we can figure out our mean squares. Mean squares between is going to be a calculation of between sums of squares divided by between degrees of freedom, and that's going to give the value that goes here in the mean squares between. And so over here on my worksheet you can see I've written out that formula for mean squares between, and now I can just plug in my numbers. I've got the 1253.68 in sums of squares between divided by 3, and that gives me a 417.89. And I'm going to put that in the mean squares between. And then mean squares within, I've calculated sums of squares within is this top number, and the degrees of freedom within at the bottom number, and so I'm going to divide, and I'm going to get a 104.52. And I encourage you, as I'm working through these problems, to pause when you need to pause the recording, the video when you need to, and make sure that you are actually calculating these yourself. You're not just watching me do it, but that you're following the steps, because it's in the it's in the actual working of it that you get into a habit of how to do this through practicing. Okay, so please have a sheet of paper out and be doing this and pausing as you need to and checking your work and seeing where things went wrong, if they do go wrong. Okay, so now we have calculated our mean squares between. That should have a 417.89 in it, and mean squares within, which is a 104.52. And so now we have all that we need in order to calculate our f obtained. And this is going to be the number that comes in this box is going to be the number that we use to test our hypothesis. So for f obtained, on my worksheet over here on this side of the PDF worksheet, I can see that I have f obtained is equal to mean squares between divided by mean squares within. So I can just plug in my numbers there. 417.89 divided by 104.52, and I get an f of a 3.998. Okay, so I can put that number in there. Now I'm going to go ahead and click to the next slide because I've now filled in all of our calculations. And we can see I've just filled in those numbers here so that we have it in our source table. Now that I have that, let's go back up to those questions that were at the top and begin to answer them. So the first one asks, how many groups are in this experiment? Now remember that the number of groups in the independent variable is noted with the symbol k. And we know that the degrees of freedom between is k minus 1, or the number of groups that you have, minus 1. So given that, if we have 3 degrees of freedom between, we know that k has to be 4, because k minus 1 equals 3, 4 minus 1 equals 3. So k equals 4, and that tells us that there are 4 groups, or 4 factors in our independent variable. Okay. So the second one uses the same kind of logic using our understanding of degrees of freedom. So assuming an equal number of subjects in each group, how many subjects are there in each group? Well, to do that, we're going to look at what's our total, how many subjects overall do we have? Okay, and so we know that what we're looking for is n, the big N, total number of subjects. And we know that total degrees of freedom is big N minus 1. Okay, n minus 1 up here, and that is equal to 39. So that tells us that n is 40. And if each of our 4 groups has an equal number of subjects, we would take 40 divided by 4 and get 10 subjects per group. So that would give us an equal number of subjects per group with a total n of 40. So little n equals 10. Alright, for this next question, we actually are going to take some information that we have from our table, but we're also going to need to use the table, the F critical value table in the back of your book. So we want to know what the critical value of F is if alpha is 0.05. And remember in your table that alpha equals 0.05 are going to be the non-bolded numbers, and alpha equals 0.01 are the bolded. So we're going to look at the non-bolded numbers. And the next piece of information we need is we need to know our degrees of freedom between and our degrees of freedom within. So we're going to go across the row till we get to 3 in our critical value table. So horizontally we're going to go to 3, and then we're going to go vertically now under 3 down to 36, which is our within. And there should be a number there which, if we pick the right one, should be 2.86. Okay? So take a moment and find that and make sure that you know what we're looking at there. Okay? So now that we have our critical F value, we are going to do the same hypothesis testing we've been before. We're going to find out, is our F obtained? We're going to compare it to our F crit and find out, is it in our critical region? Now recall that for an F test, it's a one-tailed test, and we always put our critical region in the positive tail, or the tail of it. So we're going to put it in the positive end. So we're looking for any number that's equal to or greater than 2.86, or our F crit value. So we're going to compare our obtained F, which is a 3.998. Is that greater than or equal to 2.86? Yes, it is. So that means it's in our critical region. And we can then, because it's in our critical region, we can reject the null and accept the alternative. And of course our alternative is that the null is false. So we know there's some kind of between group differences in this study, but we don't know yet where those group differences lie. Okay?